In this example, we're going to try to visualize what we mean by partial derivatives. So here we have a graph of some function of two variables. It doesn't really matter what the specific function is, but here we can see we have a 3D graph. So what we are asked to do is to determine whether the given partial derivative, so the ones that are listed at the bottom here, whether they're positive, negative, or zero. So it's not asking us to compute it because that would be a bit more challenging. All we are asked to do is to figure out if it's positive, negative, or zero. Now it has a note here that the function is symmetric about the point 0, 0, or it's symmetric about 0 in both the x and y directions. Now that might be a little confusing right now. We're going to get back to this. I just want to show you the question, and I want to connect this to what we already know in 2 dimensions. So let's think about regular functions of single variables. So if I draw an axis here, x and y. And now the specific function doesn't really matter. Let's say I have something that looks like this. Now if I ask you, what is the sign, so is it positive, negative, or zero, of the slope of the tangent line that would be right around here? Well, that's simple, right? We know that's positive. It's going up. Now, if I asked you something over here, we know that means it's negative. And if I said something right about here, we know that would be zero. Now, I want to connect something to the three-dimensional space and just show you something that might be a little confusing at first. Let's say I flip this. Let's say I had written y is the same way, but now I'm saying x is here. But this is not the negative x direction. This is still positive x. I just almost flipped this or reflected what we drew over here. And now, let me just copy over. This is not going to be the same function, but let me just copy over something here for us to visualize this. So now, if I showed you this tangent line here, right, immediately you might think, oh, that's positive. But you have to remember, we flipped this. The positive x-axis is facing the way that it usually does. Here it's facing left. Usually it faces the right side. So really this is negative because it's going down if you're thinking about x increasing. 0 is still going to be 0, obviously, but then when we talk about this, which looks negative, this is actually going to be positive. And I think you probably understand this concept. It just might be a little unfamiliar right now. Now, why am I even bringing this up? Well, because when we're looking at a three-dimensional graph, it's important to have a grasp of visualizing and to be able to realize where's positive and where's negative. And we're going to see this exactly in a few seconds. So since now we've reviewed that, let's go back to this graph here. And let's think about the first question. So the first part here asks us about the partial derivative of f, this graph, at the point 2, 2. Now, when it says the function is symmetric, what it means, visualize it like this. So imagine you rotate this cube, or this, it's in a cube, that's how it's showing it to us, or what looks like a cube anyways. If you rotate that so that way this face faces you, directly faces you, you could imagine that you have some sort of shape that's kind of bended downwards. Okay, so we got that. Now, let's think about another side. Let's think about this one. If we looked at this side, the y, so we were in front of the y-axis in that sense, we'd imagine that it's now bent upwards. So I hope you can see that. And they're using some hues of different colors for us to kind of visualize this. So hopefully you kind of understand the symmetry that's going on here. Now, when I break it down, I think it's going to be even more clear. So let's think about this first question. So let's go to the point 2, 2. So this is what I meant about the x-axis. We have to realize that this is the way x is moving and this is the way y is moving. Okay, so let's plot this point. So here's 2, here's 2. Let's see, it seems like it's somewhere about here. Doesn't really matter if we're plotting it exactly because, again, we're not trying to calculate the specific number, just that if it's positive or negative or 0. Okay, so we have our point. Now what does it mean by the partial derivative with respect to x? If we were computing this, we know that we pretend y is a constant and we differentiate with respect to x, as if x was the only variable that we're concerned about. So that's essentially the same thing we're doing here. We're going to hold y constant. So y is currently 2, and we're going to assume it's 2 for every x value. So in other words, we're almost thinking of a plane at y equals 2. So now if we took that plane and we intersected this graph, if we sliced this three-dimensional graph, what kind of line or what kind of curve would we generate? You could imagine it would look something like this, almost like a parabola. We generate a two-dimensional curve because we're keeping y fixed. So really we only have two variables now. We have x and z. We're not too concerned about z right now, but when we hold y constant, that's what happens. Now why is this useful? Because now we have to visualize this. Since we already took care of that partial component, we can now look at this yellow curve I drew here and pretend it was just a normal curve like the one down here, a normal flat curve. And now ask ourselves, what's the derivative like at that point, at this point here? What's the derivative right about here? Sorry, not there. I don't know why the arrow went there. What is it right around here? Okay, so let's draw our tangent line and try to visualize this. So something like that. Now you might think, to me anyways, I thought that's positive, but remember, the x positive direction is this way. So really we're going downhill. So let's just review that again. We plotted the point, we found that it was here. We realized that, okay, we're holding y constant. It's almost like we're walking along the x-axis, fixed at y equals 2. We realized that the curve we generate kind of looks like this parabola. Then we realized that, okay, if I'm at that point, and this was a two-dimensional graph, the derivative would be negative. Because if we move in the x positive direction, we realize that it's heading downhill. So I hope that makes sense. So the answer here is that the first partial derivative is negative. Now let's think about the y component. So let me clear the graph here. Okay, so we're going back to the same point, 2, 2, so somewhere around here. But now we are thinking about it differently. Now we are trying to pretend that x is now a constant, and we are walking along the y-axis. So we're holding x fixed at 2. Imagine a plane where x is always equal to 2 for any value of z and y, and we slice the graph. You can imagine we should probably generate something that looks like that. It's hard to draw, obviously, but you can imagine it's still kind of a parabola, but this time it's an upward, it's an open up parabola. Now what does this tell us? The way I drew it here might not be the best, so let me redraw this, because we have to remember it's symmetric around 0, 0. So really, this is going to be the next question, but where the function ends up being 0 is when y would be 0 in this case. But anyways, I'm getting ahead of myself there, so let's go back to what we were talking about here. So I drew that curve there where we were pretending we sliced it at x equals 2. And again, we're going to repeat the same thing. We're going to remember to look at the scale. We see that the positive y is going this way, and we see that if we drew a tangent line right around here, it would be positive. So essentially like what we were the way we were thinking about this before. So this is positive. Now this one might be a little bit more tricky, but I think we can work it out. So the partial derivative with respect to x, but now we have a different point. We have the point 0, negative 2, or that's the input point, I should say. So here is 0 on the x, here is negative 2. So it seems like it's somewhere over here. Okay, now we are taking this with respect to x. So again, We're walking along the x direction, holding y fixed at y equals minus 2. So we end up with something like this. Now, I know it looks confusing, but imagine rotating this graph around so that way the x-axis faces you. If you did that, this curve we drew would not kind of be on an angle, it would be straight in front of you. And you can imagine then that if I went straight across, so let me try to draw this. If I went straight across from x equals 0, I'd kind of be running down the middle of this bend, if that makes sense. And so what should that tell you? It should tell you that the derivative is 0, because there is where that curve bends. I'm saying bends because I'm trying to make it similar to how we were talking about these portions of the graph, where it kind of bends. So here, the derivative is 0. Now, finally, let's look at the last case here. Let's think about, at that same point, what happens with the partial derivative with respect to y. So again, we have the point here, but now we are walking along the y-axis. So it's going to look different now. Now we're holding x equal at 0, but we're walking along y. So it might look something like that. Now, remember, the point we're talking about here, this point is at y, it's here, y equals negative 2. So it's not where y equals 0, where it would have been 0, this derivative would have been 0. Here, because this is the positive y direction, it's going downhill. It's going downhill here. So therefore, the derivative would be negative. Now, at this point, you probably understand it fully or you're very confused. And I was confused too at the beginning when I was looking at this, but rewatch the video, try to think about it. I think it really helps for you to be able to visualize this graph, because if you're able to visualize it, it will be very simple for you to do, because once you do this once, you'll be able to do it for a lot of different examples.